Now we're going to talk a little bit about simple harmonic motion and its relationship to energy, which we've hinted at a little bit in the previous lecture. But let's first look at a system that doesn't have any friction or dissipative forces. So if we know a spring coefficient and a maximum distance, we can figure out what our total energy is when the spring is fully compressed, right? So at this point, we want to know the mechanical energy at the end point when we've compressed our spring. So we're going to add the potential spring energy and the kinetic energy. And we're going to ignore gravitational potential energy because our uh, mass is going to be moving horizontally. So there's not going to be any change in gravitational potential energy. But we know that the spring energy can be calculated using this equation, which we talked about in our uh, lab, and we talked about when we talked about energy. So this is our displacement squared times our spring coefficient. And we know at the end point there's no velocity, right? So that's a zero. So the total energy in the system is half kx squared. Now, in a conservative system, we would expect that energy to stay the same throughout the whole process, right? So we look at our image over here, and the green here is the potential spring energy, and it's going to go from a whole bunch, level E, down to 0, back up to level E after one full oscillation, or half an oscillation actually, as it gets to the other max, and then pass through the middle again where there's no spring energy, and back to its original max. On the other hand, the kinetic energy is going to be 0 when we're at the max displacement, right? Because the mass has stopped moving, and at our maximum kinetic energy when we're passing through equilibrium. If we sum these two energies up over this whole period, we get a straight line, and that is our total mechanical energy. So at the midpoint, right, at a place like right here, we expect a lot of kinetic energy, and in fact 0 spring energy. So we make this value 0. And then our ME mid is just half MV squared, or half MV max squared. Now, because the energy stays the same, right? Here all our energy is spring, here all our energy is kinetic, but they're the same amount of energy, we can set them equal to each other, like so. Now, what can we do with that equation? It allows us to solve for our maximum velocity for a system. Okay, so we can solve for V max by moving this 2 to the other side of the equation, moving the m to the other side of the equation, and taking the square root. So this is our equation for the maximum velocity in a conserved, spring-driven, simple harmonic oscillation. And we want to just look at this for a second and think about, well, what leads to a high velocity? A large K, a large spring coefficient, a large displacement, and a small mass. The smaller mass we have, the larger we're going to find is our maximum velocity. Now, a lot of systems with springs in them are not conservative. In other words, the energy dissipates over time. And we call that damping. And damping, usually we think of friction as a negative, but damping can be quite useful. We ask here, why would you want the oscillations caused by a car's suspension system to be damped? Well, you don't want to go over a bump and be feeling the up and downs of that bump a mile later. You want the car to absorb those bumps and give you a nice smooth ride. And so that's what damping can do, right? You get a displacement here, you go over the bump, and instead of continuing to oscillate, at its full strength, that oscillation will get smaller and smaller over time. And we have 3 kinds of damping. This is a picture of underdamping. What this means is that the oscillation continues, it just gets smaller over time. a critically damped oscillation, you get a 1 displacement, and then it moves back as efficiently as possible to equilibrium. So instead of oscillating back and forth, it goes from its max and then sort of makes its way as quickly as possible to x equals 0. And then finally, we have an overdamped system in which we make a displacement and there's so much friction that the mass has trouble even getting back to that equilibrium. The last thing we'll talk about with simple harmonic motion is a simple pendulum. Just to note that this is another kind of simple harmonic motion. Here our restoring force is provided by gravity. So as the pendulum mass rises up, there's going to be a portion of the weight force that's going to be pulling it back towards the center of the system. Okay, we can do some of the math, and we won't go through it here, to find our time period. But we find an interesting result when we want to figure out the time period of a pendulum. And we find that it's 2 pi times the square root of L over G. Now that's interesting, right? There's no mass in there, and there's no displacement. There's no how high did I pull the pendulum. There's no how much does the pendulum weigh. And this can make this a particularly useful simple harmonic motion because it's so dependable. Okay, so on a grandfather clock, when I use a pendulum, as long as I set the mass in the right place, and as long as I don't move to another planet with a different gravity, my time period is going to stay the same for the clock. So I can adjust, if my clock's running a little slow, all I do is change L by a little bit. And so that's simple harmonic motion.